All right. So the first thing that we want to talk about today is actually like how do we acquire and record data from physical signals. So first of all, we want to get a few bits of like terminology defined. So you'll see these phrases, and I believe these mainly come from like engineering signal theory. So we'll refer to things as transducers or sensors. Honestly, more often you will use the term sensor just because that's what everyone's used to. But in this context, a transducer is anything that will convert a signal from one form of energy to another. So, obviously in this case, we're going to be talking about turning physical signals into electrical signals primarily, but it could also be the reverse, where you're taking an electrical signal and converting it into, say, a heat signal, a heater in that case. A sensor is more of a subset of all of your types of transducers, because it's something that actually, in this case, what we mean is something that detects, measures a physical property and then records it. And obviously in this case, since we're dealing with electronic storage, electronic signal processing, what we're going to be concerned with are sensors that, like I said, react to a physical property, temperature, pressure, humidity, altitude, and convert it into an electrical signal, because that's how we're going to process and record our data, is electrically. And then just one quick thing about the term transducer. So you'll often run into sensors that are called transducers, right? Usually it's, you'll hear pressure transducer or an ultrasound transducer, sometimes with sensors that will measure liquid levels in like tanks. And in this case, they're referring to the actual sensor itself. Even though based on the definitions that we just used, that every sensor is technically a transducer. But, if you hear someone just refer to a transducer, and they're not talking about like in a theory or a generic sense, they may be referring to one of these specific types of sensors. So broadly, you can have two categories of sensors. You can have something that is a passive sensor, where it just reacts to an external stimuli, like a bulb thermometer, for example. It just reacts to the change in temperature, the liquid inside it expands, right? You could also have an active sensor, where the sensor itself is sending out some sort of signal that causes a reaction in the environment, and you're measuring that reaction. So for example, if I have radar, I'm sending out an electromagnetic wave and I'm observing the reflected waves. MRIs, right? I'm setting up a magnetic field, I'm causing a change in that magnetic field, and I'm measuring the reaction of various substances in that MRI. Right. So these are sort of the two basic types, right? I can either just passively observe, or I can probe and look for a reaction that I'm going to analyze. So you can have sensors that measure, basically any sort of quantity. In particular, the board that we use sort of as the basis for the payloads have built-in temperature, pressure, and humidity sensors. You guys have already worked with a sensor that is affected by light from the SkeeterSat. You can have sensors that are measure radioactivity, like this Geiger counter here. You can have an accelerometer, altitude. You can measure, though usually you're measuring that indirectly, right? You're measuring a pressure, or you're measuring some sort of GPS timing signal and inferring the altitude from that. You can measure the strength of an electromagnetic field, right? All of these are just, examples. And this pressure sensor right here is the old pressure sensor that we used to use in this course. It has now become obsolete and you can't buy them anymore. This example right here is a 3-axis accelerometer. So it'll measure the acceleration of this little chip in 3 different directions. And you can see the X, the Y, and the Z axes indicated on the board that it's soldered to. And then the Geiger counter here, this tube on the end is the actual Geiger tube. And all the rest of this is, support and readout electronics. And it looks like actually it's got a little beeper or clicker. So you get that nice click, click, click noise that people associate with a Geiger counter. So electrical sensors can have a variety of different outputs, right? And in fact, sensors in general can output not just electrical signals. You could have a sensor that has a mechanical output, right? A gauge that you physically read, the output is the movement of that needle. That would be, for example, a mechanical output. The SkeeterSat that you guys used earlier in the semester, that was outputting a sound signal, right? But for the rest of this course, what we're mainly going to be concerned with is signals that output electrical, or sensors that output electrical signals. So the sensors can, the signals can have a few different varying outputs. They can vary in output voltage. That one is fairly common, and often you will have circuitry that will convert other signals to an output voltage, because an output voltage is very easy to read with something called an analog to digital converter. You could have a sensor that varies the current. The simplest example of that would be something that changes resistance. That means if I'm applying a constant voltage, the current through it would vary. You can also have electrical signals that have some sort of variation with time, and those particular properties of the time variation can change. So I can have pulses that change in amplitude. I can have them change in width. I could have a repeated signal that changes the frequency of the signal. Or I could just look at the total length of the signal. These are all sorts of properties of a generic electrical signal that could be changed by a sensor that you could use to monitor something, right? This is very abstract at this point, but hopefully we'll get to some more concrete examples. Often, especially these days, you can get off-the-shelf sensors that will do, like the analog digital conversion, and what they'll actually output is some digital signal. For example, a multimeter is really this. It is something that is outputting a digital value. You can read the numbers off of it based on some conversion. What we're going to be more concerned with is our sensors that are actually going to be read out through some of the communication protocols that we're going to cover later, in which case you have to figure out how to read those values out with your microcontroller, with the Arduino in this case. So just to cover a few more concrete examples. So temperature sensors, there are many different types of temperature sensors. You guys already worked with one. You used a thermistor. That is something that its resistance changes with temperature. You guys may have heard of or used a thermocouple. That's a device where you have two different conductive metals touching each other, and they create a voltage that voltage will vary with temperature. What we're going to use eventually for a temperature sensor is a semiconductor device. We're going to use a diode where the voltage change across that diode junction is going to vary with temperature. So in particular, a PN junction diode, right, has a fairly linear range. So you can see here we have a plot of temperature versus voltage. And you can see that we have this region where it's nice and linear. So where this would be a good temperature sensor, right? Because we can easily establish a relationship between this voltage across the diode and the temperature of the diode itself. And just for example, roughly it's about 2 millivolts per degree Kelvin or degree Celsius, right? The step change in Kelvin and Celsius is the same. But you can see that it's a decreasing linear relationship in this case. When it gets hotter, the voltage drop gets lower. Pressure sensors, usually the principle behind most pressure sensors is you have a pressure across something that's flexible, like a diaphragm in this case. And the difference in pressure causes that flexible object to deform. So in this case, you have a diaphragm made out of a conductive material, and as it deforms due to a change in pressure, there's another piece that's below it with conductivity. So the conductivity in of the sensor, which is then read out as a voltage, is going to depend on the pressure. Usually, because there's also a temperature effect for those measurements, you have to have some sort of temperature compensation. Luckily, the sensors that we're going to use have built in as part of the sensor, they will automatically compensate for temperature. One thing that's important to note about pressure sensors, so pressure is always a differential, just like voltage is always, this is X volts higher or lower than this, right? So pressure is, you're measuring the difference in pressure across the two sides. What we're going to use is called an absolute pressure gauge, which means that it's basically referencing the pressure in comparison to an absolute vacuum. So you can see there's a little tube here, and that's what's actually sensing the ambient pressure. And inside of this device, there's basically a section that has a vacuum in it. So it's going to measure the difference between the ambient pressure and that vacuum. You can see that there's actually another little circle here. So there are versions of this thing that basically have two tubes coming out of it. And what it will measure is the pressure difference of whatever's in those two tubes. So if they're both, out to the ambient pressure, that means that that pressure difference is going to be zero because they're both hooked up to the same pressure. But I could, for example, have one side hooked up to ambient pressure and the other side hooked up to some sort of enclosed pressure vessel. So the third sensor that we're going to give you as part of your Megasat kit, or third type of sensor, is a humidity sensor. So one common way of doing this is you basically have a small air gap that acts as a capacitor. And the particular dielectric, or sort of how the electricity gets pushed across that gap, is going to depend on the humidity. So it'll have different readings at dry air versus humid air. And so you can measure the change in that conductivity or the change in that capacitance and infer the humidity from that. One thing that's important to note about some of these is that they are light sensitive, i.e. if I shine a light on that, that's also going to cause a change. So you need to keep it out of the light. So this particular model here, I believe, is the humidity sensor that we are going to send out to you guys in your Megasat kits. You're also going to have this, what's called an IMU, an inertial measurement unit. What it'll tell you is acceleration and orientation. In this case, you basically have a small mass that's sitting sort of on a beam. As it gets accelerated, that gets bent, that changes a voltage. This works sort of similar to the pressure sensor in that you're causing a very small mechanical deflection to create a change in an electrical signal. And so basically you have to sort of have this little test mass connected to 3 different axes, or have 3 different little test masses. And as it gets accelerated in a particular direction, you cause a change in voltage. The other, in addition to the accelerometer, these devices have a gyroscope. So what that does is basically measure rotation about the axes, and they'll give you a readout in a degrees per unit time, like degrees per second. And that's how quickly it's rotating about that X, Y, and Z axis. And sort of the way that these things work is, it's a bit complicated, and honestly, I'm not an expert on this. But you're having the Coriolis effect, where you're accelerating a reference frame, which means you basically have a force that wants it to go out. And in this case, that's going to cause a change in capacitance. If you want to read up on these, what these are actually called, vibratory MEMS gyroscopes. But like I said, I am by no means a expert on these things. But this particular board is one of the boards that you'll get on the Megasat kit, and you'll be able to interface with this to get accelerations and rotation rates if you want. So with all of these sensors, you have this output signal, some sort of raw output signal coming out of them. However, you usually have to do some sort of modification of that signal. Obviously, you or I can't inherently read a voltage signal, so you have to do some sort of change to the signal to get it into a form that you can read or record. And then also, often other electronics are not going to be able to be set up to inherently read the information well out of the signal. So you may have a nonlinear signal coming in, and you will probably want to make it linear. It may be too high, so you may have to make it smaller. You may have to lower the amplitude. It may be too small. You may need to make it bigger. Often you will have, if you're dealing with something that's very sensitive, the signal is going to be pretty noisy, so you're going to have to use some techniques to remove that noise. Most of your raw signals are some sort of analog signal. And if you're going to record that to a digital device, or you're going to use it with a microcontroller, you have to convert that to a digital format. And, you know, it may be where you're getting a lot of interference because you're not isolated from the environment. So you have to somehow try and isolate that signal. This is just sort of generic, but all of this stuff together is what you would call signal conditioning, where we're trying to clean up the signal, get it into a usable form. So for example, we have this cartoon picture where you have this noisy raw signal from a sensor, and then we filter it and get the actual information that we want out of it. So again, we want to introduce some terms here. So when we will often talk about the span and the base of a signal. In this case, I'm mainly going to be talking about voltage signals because that's what we're going to deal with more commonly, but you could apply these terms to other things. So the span is just the range of possible outputs, right? It's the minimum value and the maximum value, how wide that is. The base is the lowest possible output you can get. And what we're going to do often is use some sort of signal conditioning circuit to match the span and the base of our sensor to the device that's reading it. Because if our input signal is too big, we may not be able to read it out. We may be losing resolution because it's a very small span, but we have a very coarse ADC. So we're going to try and get these to match. And just as an example, that is, and these are actual numbers roughly, for example, the diode at temperatures around room temperature. So in that case, we're talking about the voltage drop across the diode. In the temperatures that we care about, it's going to be, between 450 to 800 millivolts. So that's 0.45 to 800 millivolts. But we're going to read it out with something that reads out from 0 to 3 volts in this case. So we have, of the sensor, it has a base of 450 or 0.45 volts, right? That's the minimum value. The span, which is just the max minus the minimum, is 350 volts. Whereas the circuitry, the ADC that we're going to read it with, the thing we're going to use to record numbers of that voltage, that goes from 0 to 3. And so the base is 0 and the span is 3. Pretty easy in this case. So we want to get these to match so that we can use that entire range of an ADC. And also you can see if the signal of the temperature sensor got higher than our reading circuitry, we could possibly damage it. Best case scenario, it would just sort of cap out and we wouldn't be able to see the changes above and below that range. So if we look at these two sets of values, I mean, what that does is that gives you the equation for a line, right? So if I want to know how to change the input to a certain output, right, I can just plot the line. And what my two endpoints of the line are going to be the two minimum values. So in this case, 0.45 and 0 volts. And the two maximum values, 0.8 and 3 volts, right? And then you have 2 points, and either I can manually calculate what the slope and intercept, what the equation of that line is, or more likely I'll plug it into some graphing software and have it give me the equation of that line. And so in this case, the slope is about 8.5 and the intercept is about -3. So what we call that equation that gives us, here's my input, here's my output, right? The relationship between the input and the output of a conditioning circuit, we call that the transfer function. In particular, for amplifying circuits, we call the slope of the line the gain, and we call the intercept the offset, right? Because I want to offset the entire signal by a certain amount, and the gain is just the output voltage over the input voltage. So the next question is okay, I know that I want a circuit that will generate this particular transfer function, that it will take this input signal and make it to this other output signal. But how do I actually do that? Well, this is where you're going to start using amplifying circuits. So to amplify a circuit, both we mean just modifying it, but more specifically, when it's too small and we want to make it larger, we call that amplification, right? You're making the signal greater. In other words, we have a gain of greater than 1. But we might also need to make a signal smaller. Perhaps it's a sensor that has a bigger range than whatever we're using to read it out with, or we're worried about possibly causing some damage. In that case, we want to make it smaller, and that's called attenuation, right? We're making the signal smaller. In this case, we mean the gain is smaller between 0 and 1, right? And this is just sort of a generic example of, hey, I have an original signal. I can either make it bigger, or I can make it smaller, right? And often one thing that is going to happen is signals are going to naturally attenuate as you send them over distance, right? It could be that it's a signal in light that gets scattered because you're sending it through atmosphere. It could be an electrical signal and you have, resistive losses in the cable between your sensor and the point where you're reading it out. So often attenuation is something that you're not even attempting to do, but because of the physical setup of your sensor is something you'll have to either counteract or take into account. So the actual piece of electronics that we're going to use to do this is something called an operational amplifier, or much more commonly, an op-amp. So these are integrated circuits. There's a whole family of these. There's many, many different types. But in general, they all have the same sort of basic function and layout. You have 2 input signals, a non-inverting input or a positive input, and then the inverting input or the negative input. And depending on what you do with the rest of the circuit, it's going to combine those 2 signals and generate an output here. And then one thing to note is, besides the signals and the output, they have a completely separate power supply. So you're going to have a positive and a negative power supply. So you can get, like I said, all different kinds. And in fact, you will often find integrated circuits that combine multiple op-amps into a single chip. If it only has one, it'll be a single. dual will be 2, quad will be 4. You will run into sort of 2 power supply configurations, a bipolar power supply, where you have a positive and negative voltage at the supply pins, and that'll usually be the same. So it'll be like plus 12 volts at VS or positive VS and minus 12 volts at negative VS. But you may also see them as a single supply where basically you have ground on the negative supply and a positive voltage on there. And there's going to be a whole bunch of different voltage and frequency ranges that these are going to operate with. That's going to depend on the particular op amp. That's often going to be what leads you to select a particular version over another. The 2 that we're mainly going to work with on your payloads on the kits and then some of the activities is this AD820, which is a single op amp, and the AD822, which is a dual op amp, right? And you can see these are pinouts. However, don't refer to this. You always want to go to the data sheet, but you can see that they're basically the exact same chip, except that this one has 2 op amps built into this, and this other one just has 1, and consequently it has a few pins that aren't really used for anything. So there's a few sort of rules of thumb if you're trying to design a op amp circuit. And bear in mind that I am not an electrical engineer. I would not basically try and design an amplifying circuit. I would probably look up an existing amplifying circuit and find the appropriate calculations to select the rest of the components based on the data sheet. But what an op amp basically does is it changes its output value to try and make the input voltages 0. So it's going to change this voltage here to match these 2 voltages. And the other thing is you do not have current flow into the input pins, i.e. there's no current flow here in or out of this pin or in or out of this pin. So the way that you do this is you have to have some sort of feedback resistor that will connect that output back to one of the inputs, because otherwise how is changing the output going to affect the voltage at one of those inputs? So you can use these rules in combination with circuit analysis techniques like Kirchhoff's loop law and node law, if you're familiar with those, and Ohm's law to figure out, okay, if I have this voltage at the input pins, what's the output pin going to read? So we're going to go through sort of some simple examples of some amplifying circuits that will hopefully make this make a little bit more sense. So the simplest version of one of these things is an op amp where the gain is just 1. The output signal matches the input signal. So that's fairly simple. You just basically connect the output back to the inverting input, and your actual signal goes into the positive input. And what you'll get is that V in equals V out. Now, you may then wonder, well, what good is that? Who cares? I haven't changed the signal. Well, what this is useful for is whatever current is getting drawn from V out, that charge is coming from the power supplies. It's not coming from V in. It's not coming from your sensor. So you can actually have a large amount of current coming out here, and you won't have any current drawn here. And that's important because one, you may have a sensor that could be damaged by excessive current draw, or you could have the situation where if I was drawing current here, that may actually affect the signal, you know, depending on maybe I have a long line where I have resistance that could create a voltage drop. Well, I don't want to have that current happen because I don't want that voltage to depend. I don't want the voltage at Vin to depend on that current, right? So this is called a buffer because, you know, it creates a buffer between Vin and Vout. Next, we have an inverting amplifier. So in this case, Vin is connected to the negative input through a resistor. And then you have this feedback resistor that goes around back to the negative input from the output. You will often have the other pin connected to ground like this through a resistor. But the transfer function is going to be this particular form right here. And you can see that it has a negative sign out in front of it because it's going to flip the voltage. If I have a positive voltage, it'll go negative. So that's why it's called an inverting amplifier. So the actual gain is determined by the ratio of the feedback resistor to the input resistor. But the actual gain number is going to be negative because it's a inversion of the signal. It flips it. So the other thing you can do is you can make a non-inverting amplifier where you don't change the sign. The input is connected to the positive voltage. You have a feedback resistor, again, between the output and one of your inputs. And then you have this input resistor that goes to ground. So in this case, you have this extra factor of 1. So this is always going to be an amplifying circuit because even if I make my input very, very large, the smallest that the second term can go is 0, right? It can't go negative. So in this case, it's just going to be, you're going to have a minimum gain of 1, but some gain larger than 0, or some gain larger than 1. I can create a summing or a summing amplifier or a summer. And what that's going to do is it's going to add, I'm going to have 2 separate voltages and it's going to add them together at the output. In this case, this is an example of an inverting adder or inverting summing amplifier. But you can also, if you wanted to, you could look up a non-inverting version. In this case, your output is going to be this linear combination of the 2 input voltages. So often I just want this to be, these 2 values to be 1, so it's simply adding it. But I could also, you know, multiply this one by 3 and this one by 1, right? By selecting particular values, again, feedback resistor from the output back to the input, and then these 2 input resistors. Another common one is a differential amplifier or a difference amplifier. So what this is actually going to amplify is the difference between my 2 input voltages. So again, feedback resistor back to one of the inputs, and then these 2 input resistors. This gets a little bit more complicated, but if I select that my feedback resistor and R1 have the same ratio as my grounding resistor and R2 here, you get a nice, simpler equation. In the end of semester project, we'll show you like what the full equation is for this. But in this case, you can see that basically I'm amplifying the difference between V1 and V2 here. So a pretty common addition that you're going to want is a offset. So like we said when we sort of first introduced this, I need to shift the entire, I don't only need to adjust this gain, I need to actually shift the entire signal up and down. So basically, each one of these circuits will have a version with an offset. And that's usually accomplished by having some set voltage come in at one of the inputs. But we're not going to go into that now, like specific examples. Again, you basically, if it was me trying to figure out a circuit, I would look for inverting amplifier with offset or something like that. One important caveat to note is that your output value is limited to be between the values supplied by the source. So the largest it can be is the value you give to V plus, and the smallest value it can be is whatever it's at V minus. So that in particular with the inverting amplifiers, you can now see why you would often have a positive voltage and a negative voltage, like plus 12 volts, minus 12 volts, because otherwise, when this gets inverted, it's just going to get set to the minimum value, which would be 0 if this negative supply pin was connected to ground. For the non-inverting amplifier, that's not as much of a case because I'm usually expecting a positive input and a positive output. But that's something to keep in mind, is that you need to supply a sufficient voltage to the op amp to get the actual output you're trying to get. In particular, if I'm trying to amplify a 5-volt signal coming in and I want to double it and I only supply 5 volts to the op amp, well, the most I'll ever get out of that op amp is right around 5 volts. It's also very common to basically have multiple stages, where I have, say, a buffer first to prevent any sort of effects of the current draw effects from affecting the signal. And then I could feed that into, say, a non-inverting amplifier or a differential amplifier. So often you'll see one op amp feed into a second op amp. And like I said, if you're trying to design a circuit, if you're trying to figure out what values you need for a resistance, you want to look at either the data sheets, or most of the manufacturers will have some sort of design document that will step you through how to pick the values for the resistance to get the actual amplification you're looking for. So besides amplification, the next most common sort of signal conditioning you do is filtering. So pretty much any electrical signal is going to have noise. And what really matters is the noise large compared to the signal that you're interested in? So if I'm looking at a 0 to 5 volt digital signal, the noise is going to be, tens of millivolts. So I really don't need to care about it. But if I have a small signal that's, maybe just a little bit bigger than the random electrical noise, I need some sort of filter circuit to remove that, try and remove that random variation. And a filter is just something that removes some part of the signal, usually the undesirable part, the noise, and then you can, or you can try and restore, correct for some sort of distortion. Usually when you're talking about filters, we're talking about something that acts on the speed of the signal or the frequency. So typically what we will do is we'll remove the fast signal, because often the noise will have, you can see here, has like a very rapid variation. In which case that's called a low pass filter. We're allowing the low frequency signal to pass through. But it could be that you're also trying to remove the slower signal, which you would use a high pass filter. You are allowing the high frequency signal to pass through. And sort of as this, again, a generic example, you can see, I have this really rapid variation due to noise. And you can sort of see, here's the signal that I'm interested about in that noisy signal. Well, if I use a low pass filter tuned to it, set to a certain frequency, I'll basically average out this fast variation in noise, and I'll just be left with this slower signal. Another sort of important thing to consider or to think about with these signals and sensors is the concept of input and output impedance. So impedance is sort of a generalization of resistance that also includes like time variation effects. And it's the resistance of a circuit to have current flow when a voltage is applied. So because it's an extension of resistance, right, it has units of ohms like you would expect. And actually the resistance is sort of part of the impedance. It's the, if you want to think about it, it's the time independent part of impedance. But it's also, impedance will also, I said, include effects that depend on the frequency. And in fact, that's how your low pass and high pass filters work, is they're going to have impedances that increase with frequency or decrease with frequency. But most often we want, or in general, circuits have a impedance on their input, i.e., if I hook up on the input sides of these, what's the impedance? And on their output. And this is not just circuits, this is going to be most of your test equipment. So for example, if I'm using an oscilloscope, it probably has a couple of settings. One, it'll say 50 ohm input, but it may also, I may be able to change the settings so it has basically a very high impedance on the input. A 1 mega ohm is fairly common. And most of your test equipment will have a similar either setting or a spec on the output. And for example, a signal generator will be 50 ohms on its output. So yeah, I have a question in the room here. So the question was, is the input impedance the same thing as the internal resistance? It sort of could be viewed as that, but usually it's not the same thing. Usually internal resistance is something you talk about in like a power supply. But I mean, it is a resistance effect that is internal to the device. But usually when we say internal resistance, that's almost always talking about a power supply. But yes. So like I said, 50 ohms is going to be very common across a whole bunch of devices. Now, why we care about this is, in general, as a rule of thumb, you want the input that is, or the output that is feeding into an input to match. That's called impedance matching, right? And the reason you want that is it can cause additional noise. Basically, you can get a signal that's somewhat reflected back. So you'll see if it's a time varying signal, you'll get it echoing. But most importantly, if you match the input and output impedance, the signal at the input is going to be at its maximum. You'll be sending the maximum amount of power into the input, right? Which means we're getting the biggest signal out that we're reading out. And that's why you want to try and match the input and output impedance. So for example, if I have an oscilloscope hooked up to the output of a op amp, the op amp impedance, output impedance is very high. So in general, I want my oscilloscope to be in its 1 mega ohm mode instead of its 50 ohm mode. So sort of to summarize the basic flow of how you acquire data is you start with your sensor here and it outputs some sort of electrical signal. We then send it through signal conditioning circuitry that is going to match this base in the span. It's going to remove noise. It's going to make that signal into the form that we want. We will then need to convert this analog signal to a digital form so that we can actually read it with our microcontroller, and we can store it in perhaps writing to the SD card, store it in memory, display it on a readout. All of that is going to, happen basically for every time we take a point of data. So that's sort of the basic overview of sensors and data acquisition. Do we have any questions? Yes, I have a question in the room here.
So where's the data acquisition process?
So the question was, where do the amplification and attenuation basically fall into this flow? So that's all part of this signal conditioning here. Filtering, amplification, all of that is right in this box right here.